Today we are going to connect the work done on an object to the energy given to that object. You've heard about energy before. It comes in many different forms. You've heard about it in terms of probably heat energy. You've heard of it in terms of movement. You've heard of it in terms of electricity and magnetism, sound and light. Chemical energy, like in your food. Elastic energy if you stretch a rubber band. And then, of course, nuclear energy. And then if you store something because of position, it has gravitational energy. Energy, these kinds of energy can be kinetic if you have movement involved, and potential if you have some sort of energy stored. Energy is defined as the ability to do work, but work is also the transfer of energy from one object to another. So energy and work are very closely related and connected, and therefore the energy unit is joule, just like the work unit is joule. So doing 1 joule of work on an object gives it 1 joule of energy. In previous notes, we talked about potential energy as being a form of mechanical energy, and today we're going to add one being kinetic energy. So KE stands for kinetic energy, and that's a form of energy due to motion. And kinetic energy equation is 1/2 or 0.5 times the mass of an object times the velocity of an object squared. The units for mass is kilograms. The unit of velocity is meters per second. So the unit of kinetic energy would then be kilograms times meters squared per second squared, or kilograms times meters per second squared times meter. And you might recognize a kilogram times a meter per second squared is a Newton. So now I have a Newton meter, which is also a joule. Where does an object get kinetic energy from? Well, it has to get kinetic energy from another object doing work on it. So work must be done. But if there are more than one forces and they are doing work and one's doing positive work and one's doing negative work, then maybe the energy added to the object by one thing is being taken away by another. So in order for an object to actually gain kinetic energy, there has to be net work done on an object. In past notes, we looked at how work done on an object was equal to the force times the displacement times the cosine theta. And specifically, net work would be net force times displacement times cosine theta. So if there is no net force acting on an object, then we know that the acceleration would be 0. Or in other words, the object would stay at a constant velocity. And if an object stays at a constant velocity, then it's not gaining or losing kinetic energy. So the big equation for today relates the net work to the change in kinetic energy, and it can be derived that the net work acting on an object is equal to the object's change in kinetic energy. Or another way to write this is that the net work acting on an object is 1/2 mv squared minus 1/2 mv naught squared. So again, really big idea here. An object must have a change in velocity in order for net work to be done on an object. If an object does not have a change in velocity, then there was no net work done on an object. Now, that's not the only way to find the net work done on an object. The other way to find the net work done on an object is to simply add up all the works done by all the different forces. So let's say that there's an applied force acting on an object, and there's friction acting on an object, and there's a normal force acting on an object, and then there's gravity acting on an object. So what we would do is we would then add up all of those forces. So work done by gravity. Since work is a scalar quantity, all I have to do is find how much work was done by the applied force, add it to the work done by friction, add it to the work done by the normal, and add it to the work done by gravity. And if the net work is 0, then I would expect some of these to be positive and some of them to be negative. So this being the most important slide of the day, to summarize, you can find the net work acting on, or the net work done on an object 3 different ways. if you know the net force acting on an object, you can use this equation. If you know anything about the object's velocity, or rather change in velocity, then you can use this equation to find the net work, which really comes from this equation. And then finally, if you know the work done by individual forces, then you can use this equation. You'd have to cater it to your scenario, but you could use this equation to find the net work done on an object. Let's try a sample problem. A 2,000 kilogram car moves horizontally with a forward force of 1,000 newtons and a resistive force of 950 newtons. Find the speed of the car after it moves 20 meters from rest. So let's draw the free body diagram. So here's the free body diagram. There's an applied force forward of 1,000 newtons. There's frictional force going back of 950 newtons, and then normal force and weight. So in the x direction, there is a net force, and the net force in the x direction is going to be equal to the mass times acceleration in the x direction. It's also going to be equal to the applied 1,000 minus the friction 950, or in other words, 50 newtons. So I could go and solve this the old way, and I could solve for acceleration, and then I could figure out how fast it's going after it moves from rest. But I want to try using the new way to solve this problem, which is using work energy considerations. So let's take a look at the net work done on an object. So the net work done on this car is going to be the net force times the distance times cosine theta. Well, earlier I showed that the net force was 50 newtons, and I didn't write this down, but it's 50 newtons to the right. And the object is assuming to have moved to the right, so therefore the angle is going to be 0 degrees between the net force to the right and the displacement to the right. And so now what I can do is plug in the net force, 50 newtons, times the distance, 20 meters, times the cosine of 0, which is just 1. And I get 1,000 joules. So there was 1,000 joules of net work done on the car. And so since the net work done on a car also equals its change in kinetic energy, what I can do is then I can find the velocity. So net work is going to be equal to 1/2 mv final squared minus 1/2 mv initial squared. And since we started from rest, that is 0. So let's find the velocity by taking 2 times the net work divided by the mass, and then take the square root. So I take 2 times 1,000 joules divided by the mass, which was 2,000. So I get the square root of 1, which is also 1. So my velocity is 1 meter per second. So on the last example, we looked at the scenario where the object had net work done on it, and therefore it changed in velocity. This example we're going to look at is one that there's a constant velocity, so we know that there's no net work done on the object. If I look at all the forces acting on the object, I've got a pulling force, which is up, an applied force, and then a normal force, and weight. And of course, weight could be broken into its components. And this is a 15-degree slope, so this would be 15 degrees also. So this little component down at the bottom is going to be FW sine 15 degrees, where this one is going to be FW cosine 15 degrees. So what's the work done by you, part A? Well, the work done by you can be solved by doing, well, what's the force that you supply times the distance that the cart moves times the cosine of theta. And starting with theta, that's going to be 0 degrees. It's not going to be the ramp angle. The theta is going to be the angle between which way you're pulling and which way the cart is moving, and those are in the same direction. So it's going to be the cosine of 0 degrees. As far as what's the applied force, we studied this a lot, and I'm not going to draw it out with much detail, but since we're pulling at a constant velocity, then all of the forces in the x direction have to equal each other. In other words, the sum of the forces in the x direction have to be 0. And there's only two forces in the x direction. There's this one here in blue highlight, the applied, and then FW sine 15 degrees, which then means that FA has to be the same thing as FW sine 15 degrees. So I have FW sine 15 degrees times the D, which is 1.2 meters, times the cosine of 0, or in other words, times 1. And so if I take the weight, 5 times 9.8 times the sine of 15 times 1.2 times 1, I get that the work done by you is 15.2 joules. Now, I could have also solved that. Since friction was not involved in this problem, we learned earlier that the work done by an applied force is equal to the change in potential energy when there's no friction. And so I could have taken mg delta h, so I would have had to figure out what the delta h was over here, and I would have gotten the same 15.2. Then it says, well, what's the work done by Earth's gravity? Well, work done by Earth's gravity would be the force due to gravity, or weight, times the distance, times the cosine theta. The hardest one in this part is finding theta. So if I look at my free body diagram again, I'm going to highlight in green. Weight is going down, and the object is sliding up the ramp like this. And so that angle is going to actually be, let's see, green. It's going to be this angle right here, which is 15 degrees, plus another 90. So that's what that angle is going to be. 15 plus 90. So my overall equation is going to be take the weight, m times g, so we'll take 5 times 9.8 times the distance, 1.2 meters, times the cosine of 105 degrees, and we end up getting negative 15.2 joules. It says, what's the net work done on the object? Well, there's two ways to think about it. The net work is the net force times distance times cosine theta. Actually, there's three ways to think about it. So number one, there's no net force, so that gives me 0. The other way to think of it is that the net work is the change in kinetic energy, and since we're not changing kinetic energy, we're staying at a constant speed, gives me 0. And finally, the net work would be the sum of the works, which would be the work done by me, plus the work done by gravity, plus the work done by the normal force. And I did 15.2 joules of work, gravity did negative 15.2 joules of work, and then we learned last time that in this scenario, the normal force does 0 joules of work, because it's at a 90-degree angle with respect to the motion. So again, I get 0 joules of net work is done. So I put energy into the system. It left my body and went into this cart. Where did that energy go? Well, the system now has more potential energy. So that energy went into be potential energy. Now imagine I were just to let it go. When it's at the top on this frictionless ramp, what happens to that energy that I gave it that became potential? Where did that energy go? Well, at the very bottom, it would be going quite fast. It would have converted its potential energy into kinetic energy, which is what we're going to talk about next, how energy converts from one form to another. These two videos are just fun representations of energy transferring forms. Work is being done from one object on one object from another, and energy is being transferred. And so take a moment, pause the video, click on the links, and take a look at these. They're essentially Rube Goldberg machines, which do a nice job of showing how energy transfers from one object to another. And then come back to this video when you're done. When we're talking about energy, it's important to note what types of forces are helping either give energy or take energy away. And we categorize forces as either being conservative or non-conservative. A conservative force keeps energy in the same type of form, like it keeps it all mechanical. A non-conservative force will change energy, oftentimes to heat. And so friction is an example of a non-conservative force. It'll take moving energy, kinetic energy, and convert it into heat. So therefore, if there are no non-conservative forces, like friction, and the energy is all mechanical, then it'll all stay mechanical. So we're going to start looking at that scenario. In other words, if there's nothing that's going to take and change the form to a total different form, then energy is going to stay in its form. And so maybe if in case of a roller coaster, this is an animation for physics classroom. It obviously doesn't work, not a PDF, but this cart, as it would roll down the ramp, would be losing potential, gaining kinetic. And so at the bottom, it would have all kinetic energy, no potential. And then as it went up the loop, it would be losing kinetic, gaining potential, and then it'll be losing potential, gaining kinetic, etc. And then the second scenario, we have all potential energy at the top. We're sliding down, losing potential, gaining kinetics. We're going really, really fast. And then we're going to hit a non-conservative force. In other words, friction is going to be involved. And what's going to happen is friction is going to slowly convert that kinetic energy into heat until we come to a stop. So friction would do negative work and change its energy and have it lose that kinetic energy. A great way to help keep track of what's happening with the energy as we're going through some motion is something called an LOL diagram. And an LOL diagram, yes, you see it looks like LOL. What you do is you make a sort of a chart of what are the initial energies involved, what are the final energies involved, and then what objects are you keeping track of as far as their energy is. And that's what you put in the middle, the energy system. You'll see that at the bottom we've got K, which is our kinetic energy, PEG, which is gravitational potential energy, PES, which is elastic potential energy, and then on the right we have the same, but we've added the change in energy, thermal, in other words, heat. So when we start a problem like this one, a car on a frictionless roller coaster track makes it to the top of the loop, the first thing I want to do is pay attention to what system of objects I'm going to have. In other words, what is going to be in my system of objects. And I am going to put in my system of objects the cart. The Earth.